Hi, my name is Johann Kruschwitz. I am one of the developers of the GraphVar toolbox. And today I'm going to give you a little introduction of how to use this toolbox, and mainly I'll focus on the graphical user interface and want to go through all the different panels to give you some ideas what you actually can do with our toolbox and how to set everything up. In a couple of other videos which are on our YouTube channel, I introduced some workflows of or introduced the concepts of how graph theoretical modeling of brain connectivity would work. And before you use our toolbox without any knowledge of graph theory, I would like to ask you please to watch also the other two videos, which will give you a good overview of the current field and maybe also a better idea of what those graph theoretic metrics actually are. Okay, so I'm already here in my MATLAB window with the most current version, 2.03. And you can just simply start GraphVar by either writing start GraphVar in here, or you go with your mouse and on the little script, start GraphVar, and run the script. So immediately you'll see something happening here. You will see the actual release date and the current version and who has contributed to this release. And you also see a little window, which is the welcome screen, where you can enter your new workspace. Just put in the new workspace name here, new, and then you hit create. But for this purpose of this tutorial, I just use our sample workspace, which is already included here, which provides you a couple of data already set up, so you can immediately try to play around with the data and to get a little grasp of what all the actual functions are doing. So I'm just going to load the sample workspace. Okay, so here you see the graphical user interface of the, let's say, the general settings panel, where you make all the specific settings of how the analysis workflow should go. It looks a little bit confusing at the first glance, I have to admit. But actually it's really ordered because we have different panels here, each subserving a different function. And I want to go through those panels right now and tell you a little bit about how you would use our toolbox for network construction. So one of the most important things now, before I started giving you some examples, is here we have this little question mark. Will enable mouse over help. If you hit this, you can just go to any of those panels, most of them, and it will tell you what you will have to do or what those panels actually mean. So here, just to give you a demonstration. So if you hover over those functions, it will show you what is actually meant by this. And most importantly, for some, you will not see any help because those were added in later versions of the toolbox. And we didn't manage to upload this yet in our help functions, but I'll do this probably in one of the next releases. Okay, so I'll disable this now again. So let's start with the general settings panel. Maybe most importantly, I will start explaining you what the file with the variables is, because this is an Excel sheet where you load in the demographic data or the clinical data of the subject that you want to analyze. So obviously you could use GraphVar only for doing some network extractions, so calculating some network topological properties and then exporting those. But the best thing about GraphVar is that we have a statistics core and also machine learning core where you can use the graph theoretic metrics that you compute with GraphVar for doing some, let's say, group analysis or single subject prediction. So what you would want to have is always a file with the variables. If you put in here, hit the select button, you will be pointed to the current workspace you're in. In our case, it's the sample workspace right now. And here, this would be this sheet, the variable sheet, which is already loaded in for me with the sample workspace. But I'm just going to show you how this looks like. So this could be a variable sheet where you have one column with the subject ID. So this should be the subject name, right? This the identifier for the subject. So there shouldn't be any overlappings between the file names. And then you have a couple of variables that you can put in. So it's basically like an SPSS. Most importantly, if you have factors, so between group factors, you do not have to encode them with 0 or 1 or do some dummy coding, but you can directly write the name in here, which I think is nice because it gives you immediately also then in our interactive results viewer a better idea of what you're actually looking at. Okay, let's go back to GraphVar. If you've loaded in the subjects, and I'll do this again now. So open. You'll get a little window where you can select what from the variable sheet should actually now be read in. It automatically deselects any categorical variables, but this is just to show you that it's scanning everything, whether it's continuous or categorical, and then gives you the option to load it in. So you can immediately use this as a checkup whether your data is coded in a correct way. And I'm gonna add this now. So the subject identifier I would not have to add because this is not a variable that I want to analyze. If I hit this, then everything is loaded from my variable sheet, the demographic data in here in this little window, which is called variables. So those are all the columns, the variables that we just saw in our variable sheet. Okay, so another important thing is that you would obviously want to have some data that you load into our toolbox. And you can do this in the form of pre-calculated connectivity matrices. For this, you would simply hit select subjects. Then I'm already in a sample workspace here, and I'm go to my specific data, which is stored here under correlation matrix. And I could just simply select all with Command and A and open everything up. Now it is loaded in, but before it's finished, it will ask me, hey, I detected that there are some sub-arrays in your file, and please now tell me what the array with the correlation matrix is. Here, I can then simply select the core matrix. And we did this simultaneously to the output of DPRSF or DPABI, so the very nice tool from Yan Chao Gan. So you can directly use the output of DPRSF actually for GraphVar usage. Okay, I just hit that in this subarray is my correlation matrix. And the important thing, and I'm just gonna show you now how this looks like in MATLAB. I go to the data. So this is simultaneously to what I loaded in. This is the correlation matrix. This is the name of the correlation matrix. I gave it core matrix underscores and then the subject name .mat. And this is exactly the name which GraphVar will detect loaded in from the first matrix that you specify. And then you will have to give GraphVar a hint of what this specific subject name is that it can connect the specific file, so your connectivity matrix, with the information that you have provided in the variables file. So I just toggle to the variables file again. You see here the subject identifier is sample_1. And here in my file name, it is also sample_1. And I'll tell GraphVar, hey, this is the specific part of the file name that you can use to link this specific matrix to the row in my variable sheet. And it'll automatically determine the start and the end. But sometimes if it doesn't work, for some reason, you can also put this in manually. And here you also, again, have the option to choose the core matrix array, which I just now chose by the selection, but you can also change this or override this manually. Okay, just to go back to MATLAB to show you how this would look like, I just read in this correlation matrix of the first subject. And here at the side, you see that's the core matrix, this subarray, and it will look like this, right? The diagonal is always 1 because, right, there is basically no connectivity from its one region with itself, and it's a mirrored matrix, so it's a symmetric matrix, so a symmetric network. Okay, let's go back. And now the next thing, what you would like to do is that you, okay, let's put it this way. Sometimes you do not have a correlation matrix, but sometimes you just have extracted time series for the specific nodes or the regions of your network that you extracted, maybe with DPRSF, or maybe with some other program, for example, FSL. Then you can use GraphVar to compute the correlation matrix that GraphVar will then do its computations on. For that, you do not hit the select subjects because here it's written con matrix, so it will expect that you have an already existing con matrix. But you can hit this button where it's just said con matrix GraphVar, where we'll provide you a couple of possibilities of generating your connectivity matrix. So by default, if you do not hit anything here, and then just select the generate con matrix button, here by default it will calculate the Pearson correlation coefficient among all the signals that you extracted from your regions of interest. Otherwise, if you want to do something specific, you can just hit like this button here, partial correlation, and then it will automatically tell you what it will do. Right here, it will compute a linear partial correlation. Okay, I deselect this, just show you for the sake of it. You can also create covariance matrices, and it will tell you that those are the ones that, and I'll talk about this later, would have to be used for the sparse inverse covariance matrix estimation thresholding procedure. Okay, but just to let you know that this is possible if you have the time courses extracted, then it makes sense to generate the connectivity matrix with GraphVar. Because one of the other possibilities, or good possibilities that you have, is that you'll not only get also an array, which I just showed you. There are different sub-arrays in those matrices for the subjects here. You also have the P matrix in, and where is it? P-value matrix, which is the P-value of the specific association between here time course of region 1 and time course 2. But if you get this, for example, from DPABI or DPRSF, this is most likely done by using a parametric test, so a regular parametric p-value, but you don't necessarily know that the distribution of the time courses or of your data would actually warrant using parametric tests. So if you use GraphVar, you can create random time series and a bunch of random time series. This will take a lot of time. For example, 1000, using different possibilities. In the manual, we tell you exactly what it is. And you can create random time series for building a null model distribution, which is then used to determine, based on this random data, to determine the real or the significance of the association between those two time series. And if you have this p-value, then, and I'm gonna show you this a little bit later, you can use those for significance-based thresholding. So building the connectivity matrix then by using this non-parametrically derived significance value. Okay. Furthermore, I'm going to show this in a little bit as well. You can also do sliding window analyses by simply hitting this button, and then it tells you again, okay, I'll perform sliding window analysis now, and giving the size of the windows and the steps, so of how much the window should move further in time on the time course. I'll not do this right now, but just generate a new con matrix, although I just loaded them in for the purpose of showing this in this video. But to show you how this is done, generate con matrix, then I'm again in my assembler workspace. I would go to my data. In your case, if you have your own data, you will have a folder where your signals are in, and those are the raw signals. for all my participants. Those are the ones from the sample workspace, so those are 30. I highlight all with Command A, load them in, and then it'll tell me, hey, I detected a sub-array, right, as we usually save the files. And okay, those are the ROI signals, and it'll be very, very fast. So see, now everything is done, and I have 116 regions. So that was pretty fast for 30 individuals. Now I show you how the data has to be structured if you have time series signals. So I just go into my data, the signals folder that I just showed you, and open this up for one specific subject. And here it is, as you saw, ROI signals. And here the columns, you see it's 116. So 116 brain regions. Those are the ones from the ALL atlas, which we used back in the days for generating the sample workspace. And 150 are the time points that I acquired my data. So I had a TR of 2, so every 2 seconds, one of those time points was acquired. So 300 time points. No, 150 time points, but 300 seconds. So those rows are the time points. And your data would have to be the same way as those files to be able to enable GraphVar for working with it. But the nice thing, as we provide you with a sample workspace, you can just look at our data and see in which kind of format you'll have to save it. Okay. So everything is set up now. I've loaded in the variable sheet, which I loaded in here then respectively. I've selected either my pre-calculated connectivity matrices, or I generated some time or some connectivity matrices from my pre-extracted time courses. Okay, just to let you know, there's also now another possibility which we implemented in here, and you can not only generate the connectivity matrices based on our functions, which we provide here, but you can also use some really nice functions from the BrainNet class toolbox, which came out in 2020. And you should please cite this toolbox with using those implemented functionalities from this toolbox through GraphVar. And please read the paper. There are very advanced and really, really good ways of generating now new connectivity matrices based on your imported time series. And for example, here you have grouped sparse representations. If you select any of those, you'll have specific parameters that you'll have to put in to generate those matrices. But please read their very nice paper to understand what this is actually doing. Okay. Now, I deselected this to make it a little bit clearer, again, the entire toolbox, to not get too distracted. So we've loaded in the data. I showed you what that you'll have to highlight the subject name in here. Otherwise, GraphVar will also tell you if you start running an analysis, hey, I could not find the variable or the first person in your variable sheet and could not match it to any of your data. So this will give you a hint of that maybe the sample or the subject name is not highlighted correctly. Okay, then the next thing, obviously, to do some network construction is you will actually have to define the network. And the network is comprised of nodes. So those are our brain regions, and the links. The links are the associations between the time series or the statistical association between any pair of time series, which is then in the end a connection if we speak about functional connectivity. But first we have to define the nodes of the brain network. And the nodes of the brain network are here the brain regions, and we can read those in with the brain regions file. I select this. Okay, here I'm still in the signals folder. I go back to my GraphVar, to workspaces, sample workspace. This is the brain region file, which I just simply select. And this is immediately load in here into this little window. There are some highlighted brain areas, some are not highlighted. And I'm going to show you how this brain regions file should look like. This is the brain regions file, where in the first column, here is a 1. Then there is an abbreviated name of the respective region. then there is a long name of the region, and then there are some coordinates in MNI space. The one, the first column, indicates that this region is highlighted and are already selected in here in GraphVar. So this is a good way if you want to do subnetwork analysis and do not want to enable or highlight those manually. You just have to add this vector to your brain regions file, where you can then either put a 0 or a 1. And if I go to the bottom, here you see the cerebellum. All I do not want to include this in my analysis now is put in with the 0, so it's automatically deselected in here, right? I'll have the possibility of going like right in manually here and selecting all with Command A, or maybe deselecting by holding the Command button a couple of areas that I do not want to include. So the name that you see here, which is the long name, so that you actually know, in my opinion, it was better to give you the long name here so you know what you're actually looking at. This is the one from the third column. The one from the second column we'll use in the results viewer, where we show you then also those specific areas. But there the window is not so big, so it makes sense to have it in a little bit abbreviated form. Obviously, you can also use the same name for those two columns, right? It doesn't matter. In the last three columns, those are coordinates from the respective brain regions in MNI space. You'll get those probably also easily for your atlases. So this is from the ALL atlas. And we have the possibility that we can plot brain networks by using BrainNet Viewer in the 3D embedding of the brain. And here it will use those coordinates for plotting those in BrainNet Viewer. So if you also want to do this and you have your own atlas, then you would have to add X, Y, Z, those three-dimensional coordinates here. The important thing is, if we speak now about defining the networks with the brain regions file, let's assume that you have 116 brain areas, so maybe extracted the signals for those and then generate the connectivity matrix with GraphVar, or you have a pre-calculated connectivity matrix. It is important that the brain regions file always covers the amount of regions that you actually have in your data, right? So if I just have a brain regions file with just 30 regions, but my actual connectivity matrix or my time courses were, let's say, 100, then it will give obviously an error in the end. So this should be in parallel. But what you can then do, even if you have pre-calculated connectivity matrix, as I just say, it is possible to do subnetwork analyses. You can just highlight those couple of areas that you want, and then GraphVar will remove those respective rows and the columns from your original data and just pretend that you just have loaded in the small network. So you're basically free to also then diminish your network and use a little bit smaller subparts. Okay, I select all now. If we have done this, so loaded in the variables, defined what our data is, then defined how the brain or the network should look like with respect to the network nodes, we can actually go to this next panel, which is the network construction panel, which now, besides this additional selection of those brain regions for subnetwork analyses, it will allow you to construct the network with respect to thresholding it. So, because as I showed you the connectivity matrix, I show you this again in MATLAB. So this is the connectivity matrix that I loaded in for one participant. It is basically a fully connected network where there are no zeros in it, so everything is connected with everything. And as I showed you in the previous videos on the introduction of brain network analysis, it makes sense to threshold your this fully connected matrix, because those fully connected matrices are not really likely to exist in biological organisms, maybe as the brain, because it would be really cost expensive to maintain all those links, right? And we also have some noise in the data, which is probably mirrored by some weak connections. And that's why we tend to throw out the weak connections by only keeping a couple of connections, which are most likely the strongest connections, which will make us inferences about the backbone structure of the network. Also in my previous talk, I said that it is also always important to show that you have different network thresholds. Those are the network thresholds, and you do not only compute your graph theoretical metric for just one threshold and then compute a statistical association with some clinical data, because it could be an artifact that you just find this strong association in here, but on those two subsequent thresholds, you do not find it. That's why it is good practice of using a lot of thresholds, right? Here you could go in increments from 10% of strongest links to including the 50% strongest links in the network. So this is called the sparsity, right? For point 1, it means I just use 10% of the strongest links in the network. Here I would use 12% of strongest link, the 14%, and I'll do all the calculations and all the thresholding for each participant on those thresholds. So the data is basically multiplying, but that's no cause to worry for you because GraphVar will handle this. Okay, but let's go back to the possibilities of how you can actually impose the sparsity constraint on your network now. You could use, as I just said, the significance-based thresholding. So thresholding the network based on the significance of the association of the time series of any pair of regions. If you click on this, it will ask you where is the matrix with the p-values in it. I'll say here, because it's my sample workspace, I have loaded in, and this is also what the Parby provides you, this p-value matrix corresponding to the correlation matrix. So I just select it, and it will now change the thresholds here, not to the 10%, which I just showed you previously, but to the significance level, right? So 0.05 threshold of the significance, or maybe 0.01, you can even go lower. But I'll not do this at the moment. And as I just said, if you want to do this, I would urge you to compute the connectivity matrices by using the non-parametric generation of time series for actually getting a valid inference on those p-values. The most common thresholding method to use is the relative thresholding. This is also, as I showed in my previous video, referred to normalization by wiring cost. And this is exactly what I just said. So here 10% of the strongest links would be maintained for each individual. And it is called normalization because if you look at each individual separately and you just maintain the 10% strongest links and you assume that everyone starts off with the same amount of regions, then you'll also have the same amount of links. And this is important because you do not want to compare, let's say, different groups if they have different sized networks or different amount of links, because this will then artificially give you different numbers in the network topological measures, which will just lead for you to make false inferences about this. So this is the most common used method, actually. Absolute thresholding is a way of imposing some sparsity in the network by not using the relative threshold, but to really using the absolute, and here, let's say it's functional connectivity, or the functional connectivity strength. So here I would say everything below a connectivity strength or Pearson correlation coefficient maybe below 0.01 is not considered as a link, and everything above would be considered as a link, right? And here it would also make sense to use several ones for computing the associations. But keep in mind that with this selection, you're not normalizing by wiring costs. So it can happen that different people have different amount of links. And this will, lead probably, if you have, let's say, two groups and one group has a weaker connectivity, the other one has a higher connectivity, you're just using this absolute thresholding, then you'll have different networks with different amount of links and different nodes, just by definition of using the thresholding. And you will make false inferences about the actual differences of graph topological measures, because this will, as I showed in the other videos, impact the network topological structure. Okay, you can also use a method which is called sparse inverse covariance matrix estimation. I'll not go into detail in here, but it's a regularized version of matrix construction or thresholding where it determines by means of a lasso whether a connection is present or not present here in the implemented case, and we will adapt this in the future releases. And this one only provides you with binary matrices. So you can just compute binary connectivity matrices or measures by using the thresholding procedure. But this could, for example, be used for PET research, PET research. But I'll not go into detail in here, but have a look at this paper of Wang, learning based on the connectivity of Alzheimer's disease, how this method works. Okay, then obviously you can also choose not to apply any threshold, so use the connectivity matrices as a fully connected matrix, but it will give you a warning dialog, so you have to keep several things in mind if you do not apply a threshold. First of all, not all graph matrix make sense if everything is fully connected, right? So if you have everything fully connected and you use a binary graph measure, so which would just assume that you have either a connection there or not there, then you would always have a connection, it would be one, then it doesn't make sense mathematically to compute any of those. So you have to keep this in mind, because we don't restrict you of any combination of the calculation of graph metrics in our toolbox. So this is something for you to think about. But here we give you some ideas of which ones would work, obviously just for the weighted ones. But you'll have to keep in mind that sometimes you may also have negative correlation or association values in your connectivity matrix, and some of the graph metrics cannot handle those. So this can, for example, occur if you do global signal regression. Then it artificially shifts the distribution of correlations and signals so that it's centered around 0, and then half of it will approximately be negative. That's a problem for some of the graph metrics. And if this is the case, if you do not use any thresholding and you have some negative weights in there, then you can modify the weights. So this is the second row which you see here. Here this would mean no change, take it as it is. Take the absolute weights. So if you have a couple of negative, then it will just make it positive. Or you can also say, hey, I do not care if those are negative, so please handle them as 0, so which would be no connection. This would really depend on how the distribution of your data is, what kind of pre-processing you did. There you might want to do some reading, but most of the time what is used in the literature is relative thresholding. And if you do the relative thresholding, then by using the 10% strongest links, by definition, those are not the weak links, which can be 0. So it is fine to say no change. Okay, then if we have determined what our brain regions are, what the clinical data is, how our actual neuroimaging data looks like, how we want to construct the graph for everyone, either by means of subnetwork analysis or by thresholding it, then we can go to actually do some network calculations. First of all, before I show you what we'll have to do here and give you some introduction, I want to highlight that you have here in the network construction panel the option of generating randomized subject data. So you can generate a random or a couple of random networks for each participant. Here would be the number, let's say 1000 or 100. It is always better to calculate or to compute a higher number of those null models, because similar as with the correlation matrix generation, as you see here, create random time series, you will build your null model distribution, and it is more valid if you have a higher number, right? 50 or 10 wouldn't make it really, because your significance value is based on the percentile, on the location of in which percentile your actual value is located in this null distribution, and it's only valid if you have actually a high number. Okay, but this said, you can, if you choose to generate this random subject data, you have possibility of selecting a couple of algorithms, which are the ones from the Brain Connectivity Toolbox of generating subject-specific data. There are ones which are for binary, some for weighted specifically. You can choose this here, binary or weighted. you'll have to choose this in addition, because it's threshold in the respective way and yeah, modified. But also look at what those specific functions have in their name. So maybe here it already says binary, so it wouldn't make sense to create weighted networks with a binary function because yeah, it's excluding itself, right? But you could see the rand mio, this doesn't have bin in there, so this can be used for binary and for the weighted ones. A really good model is the null model undirected sign. Sign, it means it is weighted again. This, I think, is written by Mikhail Rubinov, and this is the best function because it preserves the weight, the degree, and the strength distribution of the original subject network when generating a random network. So it's really close to the original data. In its original form, this function is really slow. But Leah, who's also one of the developers, has put a lot of effort in writing a C function, which increases tremendously the generation of this null model network. So then it's also feasible to, let's say, generate for your subjects thousands of those randomized subject null model networks. Okay, an important thing is you have to keep in mind that the original data of the subject is taken in. It is thresholded for different thresholds by using those methods. And then those matrices, before the topological measures are computed, are used for the generation of those null model networks. So I'm telling you this, if you are planning on computing some weighted graph metrics, which I'll show you here in the network calculations panel, but you generate binary networks using, let's say, this randomizer bin function, which is really fast but not so accurate, then it doesn't make sense in the end because you have computed binary matrices. So 1 is a connection, 0 is no connection. So you have random matrices with either 1 or 0. But then you try to compute weighted versions of those metrics, which wouldn't make too much sense, right? So you have to think here a little bit in advance which kind of network calculation you want to do. So if you use weighted ones where you have more information in it, which are also the ones which are used most of the time in the current literature, I think, then you also have to select an appropriate function here. I always now use the null model undirected sign, our C version, because this is, with respect to the properties of the original data, as I just said, the best way to go. Okay, I'll not do this right now, but just to let you know, already this cross connection, this is our statistical panel, the GLM, and GraphVar will automatically always perform parametric approaches, so using the regular statistics with the predefined distribution assumptions, which is most of the time normal, right? So you always assume, most of the time, those regular parametric statistics assume that your data has a Gaussian distribution. But it can also be that it's not Gaussian, but also differently distributed. For example, distribution of R values is heavily left-tailed and not Gaussian distributed. And then regular statistics will not make sense or are not valid if you have a different underlying assumption of the distribution of the data. So then it makes sense to use those null models to generate yourself a null model distribution where you can pick your differences. Basically, in the end, if you examine group differences, also the strength of your test statistic, maybe a t value or an r value, you pick this from your own distribution that you generate based on your specific data, so which is tailored to your data sets. Having said this, GraphVar computes always the parametric one, and if you want to build your null model distribution using those subject-specific random networks, then you hit here random NW, which is random network. So it will compute the parametric and in addition the random network null model distribution and give you some or allows you to make inferences based on this in addition to the parametric version. importantly, if you use random networks for having your null model distribution for the, let's say, group statistics or second level statistics, you don't have to put in anything here. The number of repetitions only is relevant for the permutations, which I'll explain in a little bit. Okay. Now, if we have defined our networks, we have maybe decided of computing some subject-specific null models. We can go to the network calculations panel, and if we select calculate graph metrics, then those options will be performed. If we deselect it, it will not be performed. I'm just telling you this because here you also have the possibility to only do some computations on the raw matrix without doing this entire network construction procedure. But I'll talk about this in a minute. Okay, we want to calculate graph metrics. And here, those are the brain graph metrics. These are nearly all that you have in the brain connectivity toolbox, so written by Mikhail Rubinov. And so those are a lot. They are ordered alphabetically. In the top, there are the binary versions. And at the bottom here, delineated by those little dotted lines, are the weighted versions. And obviously, there are some weighted versions which do not exist for the binary ones. And it would make sense for you to do, if you are not acquainted with what this actually is, maybe to look at my other videos where I give you a little bit introduction into some core concepts and how those can be categorized. But most importantly, you will probably have a look at the site of the Brain Connectivity Toolbox. So they have a very, very nice website where they have kind of a dictionary explaining what each of those functions is. If you don't have internet, but you have downloaded the Brain Connectivity Toolbox, you can go into GraphVar. The source folder, Brain Connectivity Toolbox, is an external one. And here you see BCT. And here you have all the functions which are now listed also in GraphVar. And if you just add, let's say, take one of those function efficiency weighted, you open it, and in the function there is the explanation of what this function actually does. Right? You don't have to take care about the inputs and the outputs because GraphVar is doing this for you. But here it's a definition of this specific function. So this is also how you can make inferences of what those functions actually do for you. Okay, I'm back in GraphVar now. And you can, so there are different, let's say, categories of the dimensionality of the graph metrics. There are global graph metrics, right, which characterize the network as a whole. So you just get one specific value for the entire network of the participant out. And there are also local ones, which will here compute the local clustering coefficient for each of the brain regions in your network. And then there are also three-dimensional ones, which is edge between the centrality, for example, where the respective graph measure is related to each element in the matrix, which is the connection here. So those are different dimensionalities that actually exist. And this makes sense because the results viewer is also ordered in such a way that we have a different visualization for graph metrics, either one-dimensional, two-dimensional, or three-dimensional. That's how we call it. You can also read this in the manual. If you have now selected the graph theoretic metrics that you want to analyze, you have the possibility of using those two options in the end here. There is one which is called normalized graph metric with random network. If you hit this, then your respective graph metric is, as it says, normalized by the topological measure derived through the average of random networks. And therefore, for this option, so it's basically a noise canceling tool, right? You're normalizing it against the noise. So this is basically the same kind of formula as it's also done in small worldness of those random networks. So it would not work, but I think it'll also tell you in the end, if you try to run it, that if you want to normalize with random networks, but you didn't create any random networks, GraphVar will complain. So it will tell you, hey, please generate some random networks so that I can normalize it for you. Please also have a look at the manual where this is explain a little bit more in detail, which I cannot do now, this little tutorial. You can also use the random networks to compute small worldness. And here we also need random networks because it's always the ratio of clustering and path lengths in the real network as compared to random networks. In my other video, I show you that in a random network, the clustering is really low, but the path length is really short. And in a small world network, the clustering is higher, but the path length is also shorter. And to being able to make inferences about those differences or this ratio, we need to compute the clustering coefficient. So GraphVar does it automatically if you hit this button, but to compute the clustering coefficient in the real data as compared to the clustering coefficient derived in those null model data. This term is then again divided by the path lengths in the real data as in relation to the path lengths of those random data. And if this value is greater than 1, so sigma, then we assume that there are small world properties taking part. Okay. We can also use GraphVar only for computing those network topological measures without the need of running the statistical analysis option here with the GLM or machine learning. So we can just calculate those variables and export them. So this entire streamline from here to here is working, but is then stopped at this at this panel. When you hit this panel, it will ask you where to export it to. You can say workspaces, here sample workspace, and it'll ask you whether you want to export in Excel. Obviously, this only works when Excel is installed. This is just for Windows computer, or in CSV, most likely usable for Mac, or if you don't have Excel installed. Okay, sometimes it can happen that due to the dimensionality of the graph metrics, which we have in here, the export function gets an overload and does not work anymore properly. I haven't been able to fix this anymore. But don't get distracted by that, because when GraphVar is calculating something up to this point, this will also be relevant if you then might want to look at what GraphVar is actually using for doing its statistics. Everything is saved in the workspace, in your workspace, or here in my case in the sample workspace, in the results folder. And there you have interim results, which are ordered in ascending order, right? If I would do a new computation, I would have now 14, and I already did a couple of computations in, let's say, your actual interim results folder. And then in GraphVars, there are the calculated network topological measures with the respective function name and the threshold. Okay, so don't get too sad or lost when it stops working if you see an error when you only want to exporting those values, because they are already calculated, and it might just in some circumstances be the export function not being able to write it in a CSV or in an Excel sheet. But you have it in the specific interim results folder, everything saved. Okay, up to this point we've been speaking about the workflow of network construction by thresholding networks, generating some null model networks based on those thresholded networks, and then computing some graph theoretical metrics. But this is not all GraphVar can do, because we wouldn't have to go this analysis path here at the top. We can also directly, if we have specified the settings in the general settings panel, go to the raw matrix computation panel. So we can actually disable here GraphVar to calculate those graph metrics and enable to do some calculations on the raw matrix. Obviously, you can also do both things simultaneously. It will then just be queued in the work line. Okay, what does it mean, the raw matrix? Here it says link-wise. So basically, we are not thresholding by the classical network definition the matrix in any way by applying some proportional thresholds and then computing those graph theoretic metrics, but it's rather a link-wise mass univariate approach where all the statistical analyses, which I'm going to talk about in a couple of minutes, are going to take part for each element in this respective matrix. So for example, for the functional connectivity, for each functional connectivity between any pair of the regions. This is, for example, a really useful option if you want to do network-based statistic analysis, so identify subcomponents in the network which are related to a specific effect, then you would want to use the raw matrix linkwise computations, where you do not modify the matrix per se. We still give you the option to modify this matrix, so you can also apply a threshold in this matrix, so make it sparser from the beginning. And here it again asks me for the p-value array, right? So where are the p-values stored? Because here we thresholded by the respective significance value of the connectivity of the pairs of region. Here it would make sense, as it's now obvious, to not use a predetermined p-value matrix, which is just based on the parametric kind of mathematical inference, but maybe to use GraphVar. I highlight this again here with the create random time series to actually get a grasp of what the non-parametric derived p-values will tell you. This could be a little bit more valid, the assumptions, because you do not know if your data essentially, as I just said, underlie this Gaussian distribution. Maybe it's a different one, so it makes sense to actually derive the non-parametric p-values based by those bootstrapping approaches. Okay, and those are the significance values again, similar as in the significance-based thresholding here at the top. Then we give you the possibility also to modify the weights. This is again similar as at the top here, where you can modify the weights. Either you do not change anything. This really again happens to matter depending on your pre-processing strategy or what you want to find out, whether you performed some specific data tweaking to your matrices. You could also use, again, the absolute weights, or you could set the negative weights to 0, right? This is the same thing as in the above network construction panel. Most of the time, you do not want to use any change because, for example, network-based statistics, it's a method that is specifically written to work on the entire matrix, but also with negative weights in there. So if you assume that negative weights, so negative correlations are, for example, are inhibitory connections, then you would not choose to modify those weights. Here is another possibility for you to, before the statistical analyses are done on the raw matrix, to modify the matrix a little bit. This R to Z means that, and this only works if you have matrices with correlation values in there. Correlation values are not Gaussian distributed, so they're a little bit left-tailed. And for being able, and now it's again about the parametric or non-parametric assumptions of underlying distributions, if you want to use parametric testing, so the regular statistics with the predetermined distribution where the test statistics are then drawn from based on their model, you would want to make this R to Z transform because Z distribution is centered around 0 and is kind of Gaussian. So then if you're using here at the bottom parametric tests, then it makes sense to use this. Otherwise, if you're not using the parametric ones, but you want to use random networks, then you must not necessarily transform or use the R to Z transformation, because you're building your own null model distribution where then again, based on the percentile position of the respective test statistic, inferences about the significance are drawn from. So you're basically constructing your own model and your own distribution. There, it doesn't matter if you do the R to Z transform. Here again, kind of similar as in the above network construction panel, we give you some functions that allow you to, let's say, randomize or generate random networks for each individual. Again, we have here this C version of the null model undirected signed, which preserves the degree, strength, and weight distribution in the networks, which I think is the best option of being on the safe side, because then each individual random network is really close to the, just with the random rewiring, obviously really close to the original data of the subject. This is one of our own functions that is fast, but not as accurate, I think, at null model undirected sign function. Look at the manual where those are explained, okay? This in the end brings me as well to the kind of statistical analytic approaches that you can do by means of the bootstrapping approaches that we provide you. So previously I've spoken, and again here also for this above network construction panel, about the possibility of generating subject-specific null model networks. We have this here, right? So now it's gray because I didn't highlight it. So okay, now it works. Random networks. So then it would be really more tailored to the actual data that you have, because for each individual you are computing random networks, and then based off those random networks, either the test statistic here in raw matrix or the network topological measure are calculated from. Then the null model distribution is built, and based on the percentile position of the real metric or test statistic, the significance is evaluated. Those are a little bit, in my experience, more conservative, but they are more closer to the actual individuals. But it also depends on your research hypothesis if you want to use this. Another possibility is using the permutation approach. And this is basically the same if you using the upper workflow with the network construction and the network calculation, or the lower workflow with the raw matrix calculations. This permutation means ID shuffling. And then it would be important to put in here the respective number, for example, 1,000. If you want 1,000 times the subject identifiers to be shuffled. So for example, if you have two groups, and you want to make a comparison between patients and controls, then this means that the labels are swapped across groups in a random way 1,000 times, and then the same test, for example, a two-sample t-test, is computed for each of those 1,000 random groups. Then those test statistics from the random groups are captured, each until 1,000, and then from those, and this null model distribution is built. And then for the real group, right, so which have no ID shuffling, the same test statistic is drawn, and as I just said, is put into the respective null model distribution that you generated here. This is usually faster than if you would use the random networks that you generate here or generate here, but this depends on your kind of hypothesis. Okay, but what you could still do if you decide to using the permutation approach, you can, for example, use those 1,000 random networks to normalize your data first, and to calculate small worthness, or either or, and then still in the end do the second level statistics based on the ID shuffling. So this is what most people do using the ID shuffling. Also, this is how network-based statistics, as written by Andrew Zaleski, works most of the time. Okay, now I will introduce you to the statistical analysis panel here at the bottom. So right now, I'm just going to speak about the general linear model, but here we also have a machine learning possibility. So this is, we spoke about this in our second paper that we published in 2018. But for right now, we just stick with the group level inference statistics, which a GLM can be used for. So the important thing is that here we are basically constructing one huge GLM that we use for doing our calculations. So if you, for example, would use SPSS and you would do several correlations, so several correlation analyses, in the end you get one big table where each correlation analysis, for example, of age, IQ to, let's say, those exported values, are independent of each other. But this is not the case if we set up a GLM, because GLM is a big formula and we try to explain our fMRI data. So in this case, it could be the raw matrix or the functional connectivity in the raw matrix, or the calculated network theoretical measures by the respective regressors that we put in there. So and then if we put two regressors in, it will try to estimate the unique contribution of each of those regressors for our observed variable for the amount of explained variance. So then they are basically controlled for. So just let me give you an example of how this would look like with a formula. So this is the formula of a GLM. Here, Y is our data, could be the links in the connectivity matrix, or it could also be the graph topological measure that we compute. X is the regressor that we want to use to explain the variance on our data, and beta is the regression weight that tells us how much of the variance of Y is explained by our regressor. Everything that cannot be explained is going into this error term. So those are the residuals, basically the distance of the dots in the two-dimensional graph to the regression line. And if we would now simply add one regressor, it would parallel something like a regular correlation analysis. So then the beta would be similar to the correlation coefficient. But if we would add a second regressor, then it will rather be more similar to a partial correlation, where each of the influences of one of the regressors is controlled for. You have to keep in mind there are things like multicollinearity. So if two regressors are not orthogonal, so are correlated, then one of the regressors could basically steal the variance explanation of the other one and gets a really high beta, and the other one a really low beta, although they're, just for this example, explain everything for the same amount, but are still highly correlated with each other. You have to keep in mind that this can actually happen. Okay, then we just go back to GraphVar, and before I now want to show you that we can, like this, easily drag and drop the variables into the specific fields, I rather want to show you this from a little PDF that we deliver with GraphVar. So here, if you look into the GraphVar folder, you have a couple of different PDFs with different presentations I made, where you can study all the functionalities of the toolbox independently and in your own speed. And this one is from the GraphVar, from the news from GraphVar, from the GLM when we introduced this. And this is just to show you that the between covariates selection field would mean that you have to enter continuous variables in there, for example, age or IQ. And importantly, and as I said, here we estimate regression coefficients, right, with regard to the dependent variable. In this example, we would have added now two regressors, and we'll get the unique influence by means of two betas for those variables. But what I once meant to say is, prior to all analyses, the covariates are demeaned to eliminate collinearity with the intercept term. This is good practice in GLM. Okay, between factors means that you'll have variables with which are categorical, right? So could be two groups, but it could also be three groups or up or more than three groups. But most importantly, they're not continuous, right? For example, sex, male, female. And it will estimate those effects of those categorical variables, but also compute individual group means and also pairwise differences between the groups. So it'll do the entire package for you. Nuisance variates means that those are variables that you want to account for, so where you think that they have an influence on what you actually examine. And important for you, they are not part of the GLM. They are partialed out from the dependent variables, so either from your original connectivity matrices if you're using raw matrix calculations, or from the network topological measures if you're using the classical classical way of constructing networks by thresholding and then calculating the brain variables. So those are partialed out from them before the actual GLM is set up. This is important for you to know. And we allow you, depending on how many regressors you put into the GLM, also to compute interactions between those factors. Here, within covariates means that we can do longitudinal analysis, so up to 2 time points. For example, you have a treatment you measure before and after this, and you want to examine the change of, let's say, functional connectivity or real network topological measure. I'll make a different video for that, where I'll also show you what kind of examples or ways of statistical analysis for longitudinal data we can do here, how this is done exactly, and most importantly, how we would have to structure your variable sheet, because this is a little bit different, because you have to add something that is a within subject identifier. So GraphVar would know which is the same subject at 2 time points. Okay. If we now speak about the GLM, I just also want to highlight here, this is a different presentation, what we can actually look at. If we have a D, here those are the little boxes you will then see in the results viewer. This results viewer I'm going to show in the next video. D means different between groups. If you just have 2 groups, it would then be a T for a T value due to degrees of freedom. If you have more than 2 groups, you will have the F value here. You can have, if you, for example, just do like a regular correlation analysis, just adding 1 regressor or a multiple regression by adding multiple continuous regressors, then you could have B as the standardized regression weight, right? It will always be the unique influence, as I just told you, if you have two regressors. The T would again then be the T value. P would be the significance, whether this regression weight would be would be significant by means either of the parametric or the non-parametric way of how you computed it. You can also, if you see an M means the group mean. So if you do a group comparison, for example, sex, you'll have then GraphVar automatically will compute the mean for each of those classes, but also provide you then with the difference. So this is you can select this by a drop-down panel, what you want to look at. But most importantly, you can also look at difference between standardized regression weights. For example, if you add an interaction and you have a continuous variable, which is age, and the interaction by sex, which is a categorical, then you can, the difference of the betas, so the difference for the beta of male or difference of the beta for female of age, right, on the respective graph theoretic metric or functional connectivity that you computed in here. Just to let you know that we also validated our GLM that Leah implemented in GraphVar. And there is another PDF here. It's called GraphVar SPSS validation, where we just show you what kind of settings you would have to do and how to load in the data. And then we always did the same analysis with SPSS and show you that there is, with respect to the specific analysis here, linear regression or regression with interaction term or multiple group variables, we show that we actually derive the same values as you would do if you would get SPSS. So this is kind of a validation for you that you know that the statistics are really sound with our own GLM that we put in here. Okay, I'll go back to GraphVar now. And those are the variables that we loaded in with our variable sheet. And we could now put in age as a continuous variable, IQ as a continuous variable, between factor, for example, sex. And we could decide to partial out, and this is done before the GLM is set up, partial out from the dependent variables for those control for those nuisance covariates. As I showed you in the example, we can then even look at the interactions up to 3rd order. Beyond 3rd order, it's really hard to interpret. That's why we just offer this until this level. Okay, if you are now done, you can control everything, that everything is really set the way that you wanted it to be, and then I just why not leave those in? But let's take out the IQ and let's do permutation, so shuffling between those individuals now, and with 1000, and let's hit calculate in statistics. This is the button where now GraphVar collects all the settings that you have made in the GUI and runs its analyses. So just hit it, we see the progress bar, and it is really fast. So now it's doing everything for the original networks of the individuals, setting up the GLM. And now if you see the chunks here at the bottom, if it's reached 16, it is already finished with doing all the 1000 ID shuffling between the individuals and computing the respective test statistics for those random groups. Okay, now it stops. It is preparing the results viewer and loading everything in. It should appear in a couple of minutes. And this is what I'm going to show you in one of the next videos, how this looks like. So now it's done. My computer is heating a little bit up because the room where I'm doing this recording is really hot. So it took a little bit longer, but here, this is the results viewer. In the next video, I'm going through this entire results viewer and let you know what you have to take care of and show you a little bit about the functionalities. Okay,